What if I told you that the universe has real vampires? Not the cape-wearing, garlic-fearing kind, but cosmic predators lurking in the dark, some even visible to the naked eye. The science behind these vampire stars reveals a universe far more violent and dynamic than we once imagined. These stellar parasites drain energy from companion stars in binary systems, triggering consequences that reshape our understanding of cosmic evolution. Some eventually explode with such force they temporarily outshine their entire host galaxies. Others transform into entirely new classes of stars that defy conventional stellar physics. What happens during these cosmic feeding frenzies will transform your perspective on the seemingly peaceful night sky above. Imagine gazing up at the night sky thousands of years ago. Among the countless twinkling stars, one peculiar light caught the attention of ancient astronomers. Every 3 days, this star would mysteriously dim before returning to its normal brightness, as if it were winking at observers from the heavens. This cosmic oddity was so unsettling that the ancients named it Algol, the demon star, a fitting title for an object that seemed to possess supernatural qualities. The Egyptians and Greeks meticulously documented Algol's strange behavior in their astronomical records, interpreting these regular dimming events through their mythological frameworks. The star became embedded in their cosmic narratives, associated with darkness and misfortune, even representing the eye of Medusa in Greek mythology, whose gaze petrified men. These ancient observers carefully tracked the predictable pattern of Algol's dimming, recording what they believed to be messages from their gods, completely unaware they were witnessing a remarkable astronomical phenomenon. Fast forward to modern times, where contemporary astronomy has illuminated the true nature behind these ominous dimmings. What ancient observers perceived as a single malevolent entity is actually a binary star system, two stars locked in an intimate gravitational embrace. The periodic dimming occurs when the smaller star passes directly in front of the larger, brighter star from our perspective, temporarily blocking a portion of its light in a cosmic eclipse. The explanation seems straightforward until we examine the evolutionary stages of these stars. According to established principles of stellar evolution, the smaller star should have evolved into a red giant long ago. Stars with greater mass burn through their nuclear fuel more rapidly, aging faster than their lighter counterparts. Yet in the Algol system, the smaller star maintains a hot blue appearance, rather than expanding into its predicted red giant phase, creating what astronomers call the Algol paradox. This contradiction revealed something profound about binary star interactions. Stars in close proximity don't evolve independently. Their destinies become intertwined through stellar vampirism. The key to understanding this relationship lies in the concept of Roche lobes, teardrop-shaped gravitational boundaries surrounding each star, like invisible force fields marking the territory where material belongs to one star or the other. Originally, the star that appears smaller today was actually the more massive partner. As this star aged naturally, it expanded, pushing its outer layers beyond its own Roche lobe boundary. Picture two dancers in a cosmic ballet, where one gradually extends beyond their designated space, unwittingly entering their partner's gravitational domain. At this critical threshold, material from the expanding star began flowing toward its companion in a process called mass transfer. Over hundreds of thousands of years, this stellar vampirism accelerated. The donor star lost more material, becoming progressively smaller, while its companion grew larger by consuming the transferred stellar matter. The roles reversed completely. The once larger star withered, while its companion thrived on the stolen stellar substance. Evidence of this role reversal persists in the chemical composition of the smaller star, bearing signatures of its former grandeur. The visual effect from Earth is dramatic. When the smaller star eclipses its brighter companion, Algol's brightness drops significantly, creating the winking effect that puzzled ancient observers. What they interpreted as supernatural omens, we now understand as evidence of a fascinating cosmic process, stellar evolution fundamentally altered by the intimate dance of binary stars, where one partner feeds on the other in a spectacular display of cosmic vampirism that continues to play out in our night sky. That winking effect that puzzled ancient observers is just the tip of the cosmic iceberg. What happens when a vampire star actually begins to consume its companion involves violence on an unimaginable scale. The feeding process creates one of astronomy's most spectacular structures, an accretion disk that transforms stolen stellar material into a superheated maelstrom of plasma and radiation. This feeding frenzy goes far beyond the gentle flow of material often depicted in simplified animations. As gas streams from the donor star, it spirals inward through turbulent accretion disks, where temperatures soar to millions of degrees. These cosmic horror shows reveal a star being torn apart atom by atom, as its matter circles the feeding star, creating distinctive high-energy signatures that astronomers can detect with specialized telescopes. The mechanics involve physics at extremes rarely seen elsewhere in nature. The donor star, having expanded beyond its gravitational boundary, sheds its outer layers, but this material carries angular momentum, the physical property that keeps planets in orbit. Rather than falling directly onto the vampire star, it forms a flattened disk of spiraling gas, similar to water circling a drain, but incomparably more violent, operating at temperatures and speeds that dwarf anything in our everyday experience. Through spectroscopy and occasional direct imaging, astronomers detect superheated plasma, emitting radiation across the electromagnetic spectrum, from radio waves to X-rays, creating unique spectral fingerprints that reveal the temperature, composition, and motion of the stolen stellar material in real time. Type B vampire stars represent particularly dramatic cases of stellar vampirism. These massive blue stars spin so rapidly from consuming their companions' material that they develop distinctive rings of gas around their equators. With each feeding, these cosmic predators gain both mass and angular momentum, causing them to spin faster and faster until they reach rotation speeds that would tear apart ordinary stars. The power dynamics in these cosmic predator-prey relationships recently took an unexpected turn with discoveries from the University of Leeds. Many vampire star systems contain a hidden third star, a cosmic accomplice that acts as a thrall, pushing the victim star closer to the vampire through gravitational influence. In these triple systems, the third star disrupts orbital stability, often resulting in one star's ejection while simultaneously forcing the remaining pair into closer proximity, creating perfect conditions for the vampire's feast to commence. The most catastrophic feeding scenarios occur in systems containing white dwarfs, dense Earth-sized remnants of stars similar to our Sun. When these stellar corpses accumulate hydrogen from their companions, pressure and heat build until triggering a thermonuclear explosion. These novae blast material into space at thousands of kilometers per second, creating brilliant flashes visible across vast cosmic distances, yet both stars typically survive, allowing the feeding cycle to begin anew. Evidence of this stellar vampirism appears throughout our galaxy in various forms. Astronomers have documented cases where companion stars have vanished completely, consumed without a trace by their ravenous partners. Perhaps most telling are the Blue Stragglers, stars appearing impossibly young compared to their neighbors within the same cluster. These cosmic anomalies stand out because they seem to have found a fountain of youth, rejuvenating themselves by siphoning fresh hydrogen fuel from unfortunate companions through cosmic vampirism. These blue stragglers, with their rejuvenated glow, represent just the beginning of stellar vampirism's dramatic consequences. While some vampire stars extend their lives through cosmic cannibalism, others face a far more explosive fate, one that creates a flash so bright it can be seen across billions of light years and fundamentally changes our understanding of the universe itself. When a white dwarf, the dense stellar corpse of a once normal star, feeds too greedily on its companion, it triggers one of astronomy's most violent spectacles. These stellar remnants have an invisible threshold called the Chandrasekhar limit, 1.4 times the mass of our Sun. It's a cosmic point of no return. As the vampire white dwarf siphons material beyond this critical mass, the immense pressure ignites a runaway thermonuclear reaction. The star detonates in a cataclysmic Type Ia supernova, erupting with the energy of 100 billion suns. The remarkable feature of these explosions is their consistency. Type Ia supernovae achieve almost identical peak brightness wherever they occur, momentarily outshining entire galaxies before gradually fading. This predictable luminosity transforms these cosmic catastrophes into standard candles, precise measuring tools that allow astronomers to calculate vast distances across the universe with unprecedented accuracy. Through cosmic irony, these destructive acts of stellar vampirism became the very tools that revolutionized our understanding of cosmic destiny. By measuring the distances to remote galaxies using Type Ia supernovae, astronomers made a shocking discovery in the late 1990s. The universe isn't just expanding, but accelerating in its expansion. This revelation led to the identification of dark energy, a mysterious force pushing the cosmos apart against gravity's inward pull. Stellar vampirism manifests in even more extreme forms beyond typical predator-prey relationships. Consider VFTS 352, located about 160,000 light-years away in the Tarantula Nebula. This system blurs the distinction between predator and victim completely. Two massive stars orbit so incredibly close they're literally touching, creating an over-contact binary system. Rather than one star cleanly feeding on the other, These stars share approximately 30% of their material through a connecting bridge, stellar conjoined twins. The future of VFTS 352 presents two dramatic possibilities. In the first scenario, the stars may eventually merge completely, forming a single, rapidly rotating giant star. This cosmic amalgamation could trigger one of the universe's most energetic phenomena, a long-duration gamma-ray burst. These intense radiation beams briefly outshine everything else in the observable universe, visible across billions of light-years like cosmic lighthouses. Alternatively, if the stars maintain their separation while evolving, they could eventually collapse into a binary black hole system. As these black holes spiral closer, they generate ripples in spacetime, gravitational waves that scientists now detect with instruments like LIGO and Virgo. These spacetime distortions open an entirely new window into understanding the universe beyond electromagnetic radiation. What makes these stellar struggles particularly significant extends beyond their spectacular nature. The material ejected during supernova explosions becomes enriched with heavy elements, cosmic foundational materials that eventually form new stars, planets, and even life itself. The iron in your blood, the calcium in your bones, the oxygen you breathe, all forged in stellar hearts and distributed through cosmic explosions, triggered by stellar interactions. Astronomers believe that extreme binary systems like VFTS 352 play a crucial role in galactic evolution, acting as major producers of elements such as oxygen. These seemingly destructive cosmic relationships become essential components in the universe's grand cycle of creation. Through violence comes renewal, through destruction comes the potential for new life. We've come full circle in our exploration of these celestial vampires, and what's most remarkable isn't their destructive power, but their essential role in cosmic evolution. The stellar vampirism we've witnessed represents a fundamental mechanism in the universe's grand design. Astrophysicists describe this as a cosmic dance, where stellar death gives birth to new elements and potentially new stars, a cycle fundamental to galactic evolution. The static points of light in the night sky conceal dramatic cosmic relationships. Many engage in material exchanges that echo through future solar systems, determining which elements become available for planet formation and life itself. The European Space Agency's Gaia mission reveals these complex stellar interactions in unprecedented detail. These vampire stars embody the universe's most profound characteristic, transforming destruction into creation, building complex structures from simpler components. So which is worse, a vampire star or a black hole? Let me know below. Thank you for watching. Don't forget to like and subscribe. Until next time, stay curious.